Good afternoon, students. Today we are going to talk a little bit about implicit differentiation. Implicit differentiation is a new method of differentiation that expands upon explicit differentiation that we've used up until this point. And so let's talk a little bit about how this method of differentiation is a little bit different from what we've done up until this point. So when do you use implicit differentiation? We'll use implicit differentiation in a couple of different scenarios. The first scenario is when two variables are not functionally related, okay? Instead of being a function of y in terms of x, or one variable in terms of a different variable, we might have some kind of an implicit relationship like a circle in which we don't have a functional relationship, the graph doesn't follow the vertical line test, and we probably want to use implicit differentiation as a generalization of the explicit differentiation that we've used up until this point. We'll also use implicit differentiation when two variables are implicitly a function of a third variable that are implicitly affected their value in their relationship. So my best example of this, kind of a canonical example from physics, is time, right? Time's a very good example of this. If you have a ladder that falls down a wall, the rate at which the ladder's foot kicks out from the base of the wall is related to the rate at which the top of the ladder falls down the wall. And you could think about this in terms of the effect of your marketing campaigns as you move into revenue, sales as a result of your marketing campaigns over time. Another example for business: in a competitive market, the price and quantity can be related to revenue in terms of price change. So we've done this explicitly in chapter 10.3 with example 2 on page 657. And then we've also done this in the exercise at the end of section in section 10.3, numbers 11 through 14. Lastly, this will lead us into a discussion of the price elasticity of demand. So technically, what do we need to keep in mind? When we're doing this process, we have to know that all rules that we've learned about differentiation up to this point stay in effect, okay? Derivative of a constant, still 0. The derivative of a variable with respect to itself is still 1. The derivative of a product, well, we've got a product rule to handle that. Derivative of a quotient, we've got a quotient rule to handle that. We've got a chain rule. We've got a power rule. We still have to apply all those things. All of those rules are still in effect. But the important difference is that we need to treat every variable as an implicit function of differentiation. In other words, we're always going to get an additional derivative term whenever we derive one variable with respect to another. And of all of the rules that I've just mentioned, chain rule is probably the most important one to keep in mind here, okay? I see a circle here, okay? And I'm asking you the question, can you find the slope of the tangent line to the point P, which has coordinates 3, 4, on the circle with equation x squared plus y squared equals 25? You'll notice that this particular equation is not an explicit function of y in terms of x, and you're going to need this point slope formula in order to figure out what this thing is. So the question becomes, can I find the equation of this nice little red line right here, okay? And if I'm trying to find that, well, I already know the point coordinates. I know the x1 is 3 and the y1 is 4. So I know that y minus 4 is equal to m times x minus 3. So the question then becomes, can I find this slope? Well, we all know that slope is derivative. So we need to find this slope dy dx. So what I'm going to suggest that we do here is that we take the derivative with respect to x of both sides of this equation. What equation do I mean? The equation up top, the equation that we started with, x squared plus y squared equals 25. All right, so if I do that and I take d dx of x squared plus y squared equals d dx of 25, then I may as well take the derivative of the sum on the left-hand side. That is that the derivative of x squared plus the derivative of y squared is equal to the derivative of the constant 25. Well, you'll know that the derivative of x squared, you could probably guess that that's still just 2x. The derivative of y squared is going to use the chain rule again. I'm going to take d dx of y squared, that's going to be 2y, but then I'm going to have to hit that with the dy dx. And of course, the derivative of the constant 25 is 0. So you can see that simplify out that it's going to be 2x times d dx of x, which of course is just 1, plus 2y ddx of y. That's the related rate dy dx. The change that I'm interested in is equal to 0. And of course, that simplifies down to 2x plus 2y times dy dx is equal to 0. Now, a lot of people will take a look at this particular thing, this 2x dy dx, and they'll say that, okay, that thing is going to be 0 there. Okay. Solving for the slope. By taking the derivative, we can conclude that for any choice of x and y in the circle, that dy dx has got to be negative 2x. Subtract the negative 2x, divide by the 2y. You're going to get the resultant simplification of negative x over y. The slope to any point xy on this implicit function is going to be the negative the x coordinate over the y coordinate. And what does that mean? Well, I can substitute that slope into the equation that I have written above for m. Y minus 4 equals negative 3/4 of x minus 3. Multiply, distribute that negative 3/4 through, add the 4 over to both sides of the equation, and you'll find out that indeed the equation of that red line is y equals negative 3/4 x plus 25/4. So for our second example, we have a cable company that has 4,000 customers paying $110 a month for basic cable. If each dollar reduction in price will attract 50 new customers, apparently your marketing department's been really hard at work, find the price that yields maximum revenue and identify that maximum revenue. So we already know the answer to this question from Chapter 10, Section 3, number 13, that the price is $95 and the maximum revenue is $451,250. Can we demonstrate this using implicit differentiation? And I claim that we can if we let x be the number of dollar price reductions applied to the price. Okay. Now let's start this back from basic principles. Remember that revenue is equal to price times quantity. And therefore, if I take the derivative of revenue with respect to x, that's the derivative of a product of price times quantity. Now you can see from this, the way that I've developed this, I'm probably going to need to apply when I derive a product rule. And of course, that's what I do inside of the next step. Product rules, first times the derivative of the second, plus second times the derivative of the first. So when I take an implicit differentiation, okay, that's going to be p times ddx of q plus q times ddx of p. And just simplifying that down into the derivative of quantities that we're talking about, that's p times the rate of change of q with respect to x plus q times the rate of change of p with respect to x. So the derivative of the revenue function with respect to the price changes applied, it's going to be the sum of those two quantities. So now I have to go back and I have to look at how the price and the quantity are changing with respect to x. Now remember, price was equal to 110 minus $1x. That's $110 minus $1 for each price reduction I place. Quantity is going to be 4,000 plus 50x. Each time I do a price reduction, I'm going to get another 50 new customers inside of there. And then I could get the derivative terms as well from this. Now, if I take the derivative of price with respect to the price reductions, that's just going to be negative 1. dp dx, negative 1. If I do dq dx, that's the derivative of a constant, which is 0, plus ddx of 50x, that's going to be a positive 50, right? And so now I can take these four quantities that I have over here and I can substitute them back into the alphabet soup that I have over on the left. What does that become? Well, that becomes 110 minus x times 50 plus 4,000 plus 50x times negative 1. Simplifying that down a little bit, 5,500 minus 50x plus negative 4,000 minus 50x. Simplifying that down even further, I'm going to get that to negative 100x plus 1,500. So back into basic principles, the revenue function from what I have is p times q. The derivative, what we just found there, is going to be equal to negative 100x plus 1,500. How am I going to find maximum revenue? I'm going to set the derivative equal to 0, solve for x. X is going to be 15 in this particular case. And then I could take that x equals 15 and put it back into the quantities that I have over on the right-hand side of the slide here. The price is going to be 110 minus $1 times 15. That's $95. I'm going to attract another 50 times 15. That's 750 customers on top of the 4,000 customers that I already have. Grand total quantity is going to be 4,750. And then if I want to find revenue, that's price times quantity. 95 times 4750 is $451,250 to find my maximal revenue at this particular point. So picking up with our discussion of the price elasticity of demand, suppose that in a monopoly market that I wanted to take the implicit derivative of revenue with respect to price. In other words, I want to see how the revenue is going to react as I adjust my prices up and down. If I do this implicitly, I'm going to need to treat revenue, price, and quantity as functions of price as follows. So starting off from basic principles, we know that revenue is equal to price times quantity. If I take the implicit derivative of the revenue with respect to the price, I'll do that to both sides of the equation, and I'm going to have to apply a product rule over on the left-hand side. Over on the right-hand side. So that tells me that the rate of change of revenue with respect to price is equal to P times the derivative of Q plus Q times the derivative of P. Replacing those derivative quantities as we did inside of the last slide, that tells me that the rate of change of revenue with respect to price is equal to P times the rate of change of quantity with respect to price plus Q times 1 derivative of a variable with respect to itself. That's always 1. That's what we're going to do. So this is where some smart economist came along and decided that they were going to do some algebraic Olympics, and they would define this idea of price elasticity of demand. And price elasticity of demand basically is the percentage change in quantity over the percentage change in price. And we'll see how this comes through a little bit formulaically in a second, okay? So looking at my formula over on the left-hand side, I've got that the rate of change of revenue with respect to price is equal to price times rate of change of quantity with respect to price plus quantity. What the really smart economist decided to do is factor a Q from both of those terms on the right-hand side, and there it is. Q is equal to, dRdP is equal to Q times P over Q times dQdP plus 1. And since this economist is a pretty good mathematician, he said to themselves, doesn't matter which order I add things in, so I'm going to switch up the order of the 1 plus the P over Q times dQdP. Next thing that they did was they said, okay, if I add, that's the same as subtracting a negative. So we can rewrite this dRdP as Q times 1 minus negative P over Q times dQdP. And that, my friends, is the real trick. They're going to define price elasticity of demand, the instantaneous price elasticity of demand, to be equal to that quantity. Eta is negative P over Q times dQdP. So if you're having a hard time seeing the percentage change in quantity over percentage change in price, there it is. I've just treated these algebraic quantities as divisors of one another. And you can see the percentage change in quantity up top and the percentage change in price down below on the denominator there. And it's in reference down to the dRdP equals Q times 1 minus eta. That you get some really, really interesting stuff. You see, the sign of this thing is going to be entirely determined by 1 minus eta because the quantity is always positive, right? So the sign of 1 minus eta is going to be determined by the value of eta, in fact, its relationship with respect to 1. So if eta is less than 1, then you know that that quantity is positive. Positive quantity times a positive quantity says that dRdP is positive, and that means that price changes yield revenue increases, okay? We have an inelastic market in that particular case. If eta is less than 1, if eta is greater than 1, then dRdP is less than 0. It's a negative, it's a negative quantity, right? We have an elastic market, and that means that price increases yield revenue decreases. And in the case where you have a perfectly elastic market, when eta equals 1, then we know that the rate of change of revenue with respect to price is equal to 0. And we have a perfect price since revenue is at a maximum in that particular case. At least if I adjust the price either upwards or downwards, there's going to be no change in revenue. And so I've got a perfectly efficient price in terms of maximizing my revenue. Okay, so for an example, suppose the demand for a product is given by P times Q plus P plus 100Q equals $50,000. So here we can see that P and Q, they're an implicit function. Um, Find the price elasticity of demand when P equals 401 and Q equals 99. How would an increase in price to $402 affect the revenue? When you hit next on the slide, take a second, try to come up with this yourself, and the solution will appear. So the solution is as follows, right? We need to calculate the elasticity of demand, which is negative P over Q dQ dP. And of course, dQ dP is the sticky wicket. I'm going to have to go back up to that original implicit function in order to find dQ dP. So I'll take ddP of both sides of the equation, and I'm going to come up with an idea of how I'm going to derive this first. The first thing is that I'm going to have to derive the left-hand term by term, and I can see a product rule over on the left-hand side when I take the derivative with respect to price of price times quantity. All right, so that's what I'm going to do. Take the derivative term by term. Derivative of PQ plus the derivative of P plus the derivative of 100Q is equal to the derivative of that constant on the right-hand side. Apply the product rule to the first term, plus take the derivative of the second term, ddP of P is 1, plus ddP of 100Q, that's 100 ddP of Q, and that's going to be equal to 0 because the derivative of a constant is 0. Now I'm going to replace each of the quantities ddP of Q with dQ dP, and ddP of P with respect to itself is just 1, so I'm going to get P times dQ dP plus Q times 1 plus 1 plus 100 dQ dP is equal to 0. Now I'm going to take all of the terms that don't include dQ dP over to the left-hand, from the left-hand side to the right-hand side. So I'm going to subtract Q minus 1 and find out that P times dQ dP plus 100 times dQ dP is equal to negative Q minus 1. Now I'm going to factor that derivative term out to the right so that P times plus 100 times dQ dP is equal to negative Q minus 1. And now I'm going to divide P plus 100 into both sides of the equation, find that dQ dP is equal to negative Q minus 1 divided by the quantity P plus 100, and set eta equal to negative P over Q times dQ dP. So that's going to get rid of the negative that I see inside of the numerator. It's P times Q plus 1 all over Q times P plus 100. So substituting that into my original eta equation, the P's 401, the Q is 99, so that's 401 times 100 divided by 99 times 501. We get a number which is just a little bit less than 1. That's 0.8048. I'm working with an inelastic market, and a price increase will increase revenue as well because eta is less than 1.